Hi, and welcome to Econ 481. These videos were recorded while I taught the class over Zoom, but they were later edited so that the students' faces, their questions, and my answers to those questions do not appear. As a result, the videos are shorter than a normal lecture, and they may have unnatural transitions. But I hope you enjoy them anyway. Bye now. Today we're going to talk about Roy models and late. Um, and so kind of like get a sense of where we are relative to this first part. Last class, we talked about selection and observables. We defined potential outcomes. We discussed how that was notation relative to what we call a latent variable model. We talk about causal inference, selection bias, and then we talk about selection and observables and how you could describe and identify the parameters that we typically talked about using propensity score weighting or propensity score matching or matching on covariates. As you can see, we didn't talk about estimation much, and this part of the section is not going to be so much about estimation till we get to the end. Today, we're going to talk about Roy models and late, and the idea is to start considering the case where there's selection on unobservables. And so we move away from this idea that once we condition on X, D is independent of the potential outcomes and so on. So before I get into linear AB and heterogeneity, are there any questions relative to what we discussed last time that perhaps are hanging and then you forgot to ask or something like that from last class? So today we're going to talk about instrumental variables. As you can imagine, the minute that we have selection on unobservables or endogeneity, the way to deal with that is going to be through instruments. Okay. So what I wrote here is selection on observables can be difficult to justify in economics for the reasons that we described that time. That doesn't mean that it doesn't happen sometimes or that it's reasonable sometimes, but most often won't be reasonable. So and the reason is because these variables that we typically want to study the effect of tend to be the choice of units, individuals, or whatever. And when there's choice, typically individuals will make choices with information that we don't get to observe. So instrumental variables, or IVs from now on, are going to provide an alternative for cases in which such selection on unobservables happen. And as we know, and this is sort of like the first few slides are sort of like a review of 480 with some additional elements. The two properties that you need from an instrument are typically exogeneity and relevance. And exogeneity says that the instrument has to be unrelated in some sense that we're going to describe later, and with potential outcomes. And relevance says that the instrument that we are using is related or it affects somehow the treatment that we are trying to instrument for. So in some sense, as I wrote here, may change depending on the models that we are considering. If we are in simple linear cases, then, things like conditional mean independence are going to be sufficient. But in a more general setting, we're just going to have to use versions of full independence. The basic idea in either case is the same. You need exogenous variation in the IV, okay? So that you move the IV and that changes the treatment. And then the treatment then will move the outcomes, but without having a direct effect from the instrument on the outcomes, okay? And that would allow you to identify the effects that we care about. So as I wrote here, the first part requires relevance. You move the instrument, you move the treatment. The second part requires exogeneity, because if you move the instrument and the outcome also changes, then it's unclear how much of the change is coming from the treatment, how much is coming from the instrument itself. So in linear B models and heterogeneity, so as I said, we've seen different versions of the linear B models in 480. And we studied just the simple identify, just identify IB, over identify IB, and two-stage least squares. And we also talked about GMM, empirical likelihood, and the like. All these models, like in the notation that we're using in this class, will typically take this form where you have an outcome, you have an endogenous treatment, or a variable that you really care about, and some additional controls that typically we just don't care too much about. And the idea is that these guys over here are endogenous. In our case, people are making decisions, choosing D with information that they have that we don't get to observe. As we emphasized in 480 a couple of times, unlike least squares, IB is always intended as causal. Okay, it is never descriptive, and the reason is that, remember that the first two interpretations that we provided for beta in a linear regression, mainly the conditional mean expectation and the projection interpretation, they both gave us, as a consequence of those interpretations, that the expected value of x and u was 0. So if we're really in a situation where we want to allow for the expected value of u and x not being equal to 0, it's because we are viewing the model as a causal model and not as a descriptive one. So the thing with this linear model that I'm describing over here is that if you just now define potential outcomes, okay, by fixing this d to some value, could be binary, for example, and then you do y1, say minus y0, then the treatment effect, which is the difference of these potential outcomes in this case, is just, fixed at beta, okay? And then if we allow this beta to be random, which again is something that we discussed in 480, if you remember, then things become complicated quite rapidly. Okay. So, and the reason is that the minute that you allow this beta to be random or to affect for different individuals to have different treatment effects, is that then when you start thinking about an effect, you need to start thinking whether you want to aggregate that effect somehow. You have to think about who is being affected by the instrument that you're considering and the like. And this who is just going to be very important moving forward. And if you remember, for example, the basic introduction we did to late in 480, you will remember that different instruments may affect different groups of subgroups of the population. And so the parameters that you end up identifying tend to be different. So we're going to describe all this again using the potential outcome notation. And the notation is going to be exactly the same as before, except that right now we are also going to use potential treatments, or sometimes called potential outcomes, for D. Okay, both are equivalent. And so this notation, D sub Z, is what would have chosen had Z been set to little z. Okay, and it's going to be exactly the same as before for the Y's. The observed treatment, D, is just going to be the one corresponding for the value of the treatment that you obtain. Okay? And as I said before, there are different flavors of exogeneity when you are in these more general models. But in general, exogeneity will require this instrument to be independent from the potential outcomes. Okay? And sometimes, as we will see later, we will actually need the instrument to be independent of the potential outcomes and the potential treatment. Okay. So when we're talking about instruments in this setting, we're going to be thinking about conditions like this as we move forward. So any questions about that? That was sort of like a quick review of what we did before, but hopefully if you remember, the stuff shouldn't be complicated. But if it is, you can answer any questions you have. Roy models use the latent variable notation framework, okay? And they are an alternative to the potential outcomes or potential treatment notation that we used before. The leading case of this is the binary case, and I'm just going to focus on that for reasons that I described last class, okay? But the idea of the Roy model is that the units are going to make a decision of DE, okay? And then the model takes the form where there's a latent variable that we're going to know by U, and there's an index or a threshold and a known function that we're going to call nu of x and z. Okay. And so essentially you choose one, whatever U is less than the threshold. Okay. Of course, depending on the setting, you can write as greater than or equal. Just doesn't matter. Less than or equal is convenient for writing certain formulas later. Okay. You can write this, which sometimes helps, as nu xz minus u greater than or equal to 0. right? And so when you write it like this, you can interpret this model as a utility model in which this is the utility of choosing one and this is the utility of choosing zero. And so the model tells you individuals will choose one, d equals to one, whenever the utility of choosing one is higher than the utility of choosing zero. And so this is called a Roy model. And, the terminology is kind of sometimes fleeting, or especially if you go and read the paper by Roy, which is a paper about fishing versus hunting, and you're not going to see this notation at all. But the ideas were there, and then were later developed by other researchers, and that eventually led to this formulation that is by now standard. Here, the important thing is that has this thing where you have this latent and observable U, which sometimes is later normalized to be uniform, and then there's some index that depends on the variables that you get to observe. Okay, as we did before, you can define these potential treatments just by plugging in the value of C that you care, and then that will translate immediately to say that this sort of like latent variable model translate to these potential treatments in the same way. And what I wrote here is that it explicitly models D as a choice problem. So as I wrote at the top, mu minus u is the utility of D1 versus 0 here, which is the utility of choosing 0. And so this model sometimes is convenient when you're trying to model behavior of agents, okay? Because it's sort of like puts a framework where you can think about what makes somebody go for this or go for that. And when we get to the fifth lecture in this section, we're going to be seeing how, for example, this translates to a way to think about how we can detect or not, for example, bias in decision making. Okay. All right. So a common version of this model, you can by now say maybe an old version, but still, it's sort of like a traditional common version, is to do the following. You're just going to let the potential outcomes be linear in the x's. Okay, y0 is just going to be linear in x, and it's going to have a coefficient beta 0 and an unknown b0, and then y1 is just going to be the same with ones over here, and then you're going to have the so-called selection equation. Okay, which is it takes the form of the Roy model, except that now this function u here is specifically modeled as a linear index. Okay, notice that w is just both x and z. Okay, and then all u, b naught, and b1 are unobserved random variables. So when you just write down in this model y1 minus y0, you can see that now this model gives us two parts. Okay, the first part is an observe, and assuming that these betas here are constant, an observed constant fact for everybody of a given value of x, and then it has sort of like an unobserved random component. So it allows for some heterogeneity. Okay, it's heterogeneity in the observed part, heterogeneity in the unobserved part, and then this actually, when you remember that we just don't care about the x's, what we care about is the coefficient on D. And then if we just write the you observe y as D times y1 minus 1 minus D times y0, and you work out this expression in the usual manner, what you have is that the coefficient that is multiplying D is random. And it's just B1 minus B0. And this is called a random coefficient model. Notice that this is random, but the components that multiply the x's and the product of the x's with the treatment is just constant coefficients. Okay? And so we say that there's selection on the on unobservables if u, which is what determines the decision D, okay, is correlated with the b's, which is what determine the potential outcomes. Okay? This is a way of formalizing what we described last time as units making decisions by taking into account the potential outcomes. Here is explicitly captured by the fact that this u is correlated with this b's over here. And if you just look at this for long enough, you're going to realize that this is a more sophisticated version than the first derivation that I did in the first lecture of 480 to get some random coefficient model there as well. Okay. So if you take this setting over here, this is essentially the setting in the paper by Heckman in 76. Okay. So the identification there was like, okay, we're going to take that model and we're going to assume that this B1, B0, and U are jointly normal distributed. They're independent of the covariates and the instrument C. Okay, and so identification in this model comes from something you can call well parameterization or parametric identification, where you just are careful with all your parametric assumptions, and then you get identification by just having a parametric model. Okay, as we're gonna see in a minute, this will require these variables not to be perfectly collinear, but that'll be obvious, and it's sort of like the usual thing that we need anyway. It is straightforward to derive the likelihood of this model if you write it down, but it was also it was more popular to essentially later on estimate this model as a two-step, okay, which is what became popular mainly because, as I wrote here, okay, a long time ago, it was difficult to maximize this likelihood functions on the computer, so making things in two steps was more convenient. You just think about it from the point of view of today, it wouldn't make any sense to do a two-step approach when you can just maximize the likelihood in a nanosecond. But anyway, um, this model, which is the one that is called a two-step approach in Hackman, is essentially this Roy model with this parametric structure that is identified due to the parametric assumptions that it is less efficient than the maximum likelihood, but is really intuitive, as I wrote over here. And if you just go back and read that 76 paper, you're going to see that the discussion is not exactly the one that we're having here. It's, at the time I wrote here missing data, it was like much closer to the work that, Chuck was doing at the time and so on missing data. But, you can reinterpret all that as this type of model where you really want to model selection on unobservables. Okay. So the argument in the Heckman two-step approach is the following. If you just use this parametric structure and then you consider the conditional expectation of y given w and d, remember w is x and z, then if you recall what that expression that we derived before, this is going to be x prime beta 1 plus the expected value of b1 conditional on w and conditional on d equals to 1, which equivalently is w prime gamma greater than or equal than u. Okay, and if you just work out this expectation, given that everything is here bivariate normal, then you can show that this is the covariance of b1 and u times lambda of the index. And lambda of the index is called the Mills ratio, which is the ratio of the PDF of the standard normal at w prime gamma divided by the CDF of standard normal divided by at w prime gamma. Okay. So when you look at this, what you see is that this lambda function or the Mills ratio enters the model as an additional regressor that controls for selection. So you want to, at the end of the day, run a regression that includes this as a covariate, and that will allow you to identify this parameter. Okay? So the covariance of B1U is unknown, and it becomes a parameter you recover as the slope of running regression of y on x and lambda. You can do the same for d equal to 0. You work it out. You get this expression where instead of having a minus, you have a plus, and you have the covariance of b0 and u instead of the covariance of b1 and u. And then the Mills ratio is at negative index as opposed to at the index. Okay. And then this idea, which has different versions. Imagine many years have passed since then, and different derivations and extensions. But broadly, they lead to approaches that belong to the family of control function approaches. Okay, and control function, if you just want to be very loose about it, is you're going to be able to add an additional term to your regression that is going to control for the endogeneity problems. Okay, and so the function that is controlling things here is this function lambda. So by adding another element to your regression, you control or you account for the endogeneity problem. So what's the identification argument? Under the parametric assumptions, the selection equation is just a probit, okay? And this is where Milcar said before, the probit has all the normalizations that you need and so on. Gamma is point identified, and hence this lambda, the Mills ratio, is identified as well, because if you know gamma and you know W force, and this is a known functional form, then you identify the betas and the covariance of the error terms and U from two linear regressions, okay? And in order to do so, we need X not to be perfectly collinear with the Mills ratio. And the reason is kind of obvious, because we're in a regression where both terms show up here and here. So you need this to be correlated, not perfectly collinear. Okay. So when you have an instrument, okay, the idea is that these two are not going to be perfectly collinear, because you have a term that depends on X and the other terms depends on W. So if you have instruments that are not part of the X's, then that's going to give you enough variation here to have a reliable identification problem. Okay? So what I wrote here is that in this case, X and gamma are not going to be perfectly collinear. So it's one case in which you can say that this model behaves best is if you have an instrument that you can claim that affects the treatment, which is again the relevance condition. Now, sometimes you don't have an instrument, okay, and in that case, this lambda of W gamma is just lambda X, and then you can still have identification this model without a single instrument, okay, and so because what happens is this function lambda of X is nonlinear. So it is the case that lambda and X, okay, are not going to be perfectly collinear. And so even if you don't have an instrument, you can have identification by virtue of these functions, of these two elements not being perfectly collinear. However, if you just look and plot this function lambda, you'll see that it is not very nonlinear, okay? So even though they're not going to be perfectly collinear, depending on where you are and what part of, what happens to your particular data set, they can be highly collinear in practice. Plus, the other thing that you need to think about is that we know that we are dealing with a case of selection of unobservables. And so if you manage to identify everything you want, okay, from this model without an instrument, it's because all the identification power is coming from the parametric assumptions. Because without it, we couldn't do anything, right? We have selection. We don't know what to do with it. Suddenly now, we don't have an instrument and we can do things, okay? Well, that's what I wrote here, the credibility of parametric identification, which, happens with and without the instrument, is that, essentially you can see that everything that comes from, or the most powerful feature of this model comes from the parametric assumptions. And so there's no strong reason I wrote here except mathematical convenience to choose normality. As we know, the normality makes a lot of things tractable, okay? But in principle, it should be concerning that all the identification comes from this normality assumption, which is very visible when we don't have an instrument. Okay, right now, I wrote here, at the risk of some people maybe getting upset, but fully parametric Roy models are rarely used in, recent research, good research. And when they are, they, I would say, almost always include instruments at least. Okay. So that's sort of where what could be a starting point to think about these Roy models, which is this parametric approach. But it's not where we want to go. We just want to use something else. And we're going to talk about that in a minute as we move to late. Are there any questions about the Roy model? So late comes from, I'm going to say always, a sort of like a reverse engineer question, which is, what does linear AB estimate in general? Okay. If you just grab a textbook example or like an introductory course, the linear AB model will just estimate the coefficient in a regression where there are endogenous variables. Typically, the x's in our notation is going to be the d's, and it's just going to estimate that constant effect. However, we know that a model that says that everybody responds to the same treatment in exactly the same way is not something that we are, um, you know, probably happy with in 2021. So most of the stuff that we do today tries to account for observed and unobserved heterogeneity. Okay, trying to acknowledge that people react in different ways to different medication, policies, and so on. So right now we're gonna ask the question, okay, here. What is the IV estimate with an observed heterogeneity? Right? And then here comes this magic word that I don't know if you used before this class, but it's kind of like a funny word. It's funny that the word is so popular. That tells you a lot. But an estimate is the population quantity that an estimator estimates. Okay? It's great because you just tell me your estimator, and your estimator is going to be a good estimator for the estimate. Okay? Because it's estimating that. The most important question, and the one you should always remember from today on as you grow older, is whether the estimate that you're talking about is something you care about. Okay? It's always going to be, well, you estimate something. I just give you an estimator, 1 over n sum of x times y divided by the sum of x to the power 7. Well, that's an estimator. What's the estimate? Well, you know what that is. It's just going to be the ratio of those expectations in the limit. Great. That's an estimate. And, the question that I said is the most relevant one is whether you care about that estimate. So here, that's what I said. This is sort of like reverse engineering. You're saying like, well, we don't believe that the constant treatment effect model where everybody reacts in the same way. We actually believe that people react in different ways. But let's suppose that you just still go ahead and then you estimate this using IB. Well, consider this model then. Y equals alpha plus B times D plus U. Here, B is random, okay? Because we want to allow different people to react in different ways. And then we have the selection equation. It's going to be D, okay? It's just going to be pi plus C, which is, again, random, times the instrument Z plus some other unobservable B. Okay, so here, B, C, U, and B are unobserved random variables, okay? We're going to assume exogeneity, which in this model means that the instrument is independent of U, B, and C. Okay, just go with me with that assumption. Then we're going to assume relevance, which is that the covariance between the instrument and the treatment is different than 0. And then we're going to define the SB slope estimate, okay, as the covariance between Y and Z divided by the covariance between D and Z. This is what IB estimates, right? You do IB, and then you're just going for this guy, okay? The question is, what is this guy in this model, okay? In the linear IB model, we know what it is because beta is constant, whatever, so it just gives you beta. But if we have this model, what is this guy? Well, you can show, okay, which I'm not going to do now, and it's not in this problem set, that this covariance equals the expected value of C divided by the expected value of C times B, okay? So the IB estimate is a weighted average of the causal effects of D on Y, which are these B over here, right? And the weights, okay, here, just you can write the weights are just C divided by the expected value of C. So what happens is that, again, if you just go back to the previous slide, C is, measures how much an individual changes their D as you move Z. Is a measure of like relevance. And so what this says is that agents that are more strongly impacted by C get higher weight. Z and C. I'm sorry that I say these two letters so similarly, but problem. This is Z, this is C. So the higher the C, the more weight you put to that particular individual. Okay. And then if you ask me, okay, why is that reasonable? Well, we're not talking about reasonability here. We're just talking about what it is. This is exactly what the IB estimate is giving. us. But it gives or erases some concerns on interpretation, as I wrote here. Okay. For example, consider a common instrument in the returns to schooling. Okay. Distance from college, quarter of birth, tuition subsidies. These are like common instruments you're going to see in applied papers when you want to estimate returns to education. And what you're saying here is that the IV estimate overweights returns to agents most affected by this instrument. Okay. So it's just going to assign a higher weight, for example, to those individuals that really care about distance. Okay. And those are going to, play a huge role in what you find. And it's just going to put very little weight on others that care about that list. So, and the question is, why do you care about that? Is that a representation of the overall population? I don't know. Another concern, and this is the one that sometimes people remember more, is that these weights can be negative. Okay. And this becomes now, let's call it a mathematical concern, because suppose that this random variable b over here is positive for everybody. Okay. So everybody reacts to the treatment in different ways, but everybody has the treatment has a positive effect on every single unit. Well, now you do IB and you find your beta IB is essentially 0. So you conclude that there is no effect. And why is that? Well, simply because these weights that you're using sometimes are positive, sometimes are negative. And then when you just do the weighted average, they just net out and then you get a 0. So now conceptually, this is complicated because your IB may tell you there's no effect of the treatment on the outcome, when in reality, even though there's an observed heterogeneity, you have an effect that is positive for everybody. So this raises interpretation concerns. Okay, so if you just stop here, then you say, well, the minute that I allow the model to be heterogeneous, or the minute that I allow for an observed heterogeneity, IB becomes fishy. Well, that's what Imbrins and Angrins was about. Okay. What they did is try to provide a framework where you remove that complication from the IB. And what I wrote here is that they provided additional conditions under which now this estimate, beta IB, is going to be easier to interpret. Okay. And it's not going to suffer from the problem that I said before. This paper, as you all know, has been highly influential, is used a lot in theoretical and empirical work. It's often controversial as well. And I would claim here that is misinterpreted oftentimes. People use it, but without understanding exactly what they're getting out of it sometimes. Not everybody, of course. And then, and he has this feeling that, you know what? I know how to do IB. Let's just do IB and let's try to interpret what we get, which is, again, the reverse engineering approach that I was describing before. Later, we're going to try to think in a more constructive way, which you first describe what the questions you care about, and then you see what are the tools that would be appropriate for answering that particular question. But anyway, let's just go back to Emmons and Angrist and then review the setup. So here we're going to go back to the binary treatment. So D is just going to be 0, 1, and we're going to focus on the binary instrument. Later on, I'm going to explain how this may or may not extend easily to multiple values of D, Z, or if you have also covariates that you want to add to the regression. We're going to discuss some of them, but very quickly we're going to see that the nice interpretation of late is almost restricted to this setting. I want to discuss that. The assumptions. Exogeneity. The instrument is independent of potential outcomes and potential treatments. Relevance condition. The covariance between D and Z is different than 0. So the instrument is related to the treatment that we want to instrument. And the new condition that you all know, we discussed in 480, is monotonicity. Monotonicity says that D1 is greater than or equal than D0 almost surely. And that means that anybody who chose D equal to 1 when they didn't have the treatment, they would choose D equal to 1 when they had when the instrument was equal to 1 as well. So I said it wrong, but hopefully you understood what I said. So this is the condition that is going to be magical and removing this issue that we have over here where the weights could be negative, and then even though in a case where the effect was positive for everybody, you could find zero effect. Everything is going to be driven by this monotonicity condition. So then what is the beta IB? The estimate is the covariance of Y and D divided by the covariance of D and Z. And then this, we work this out in 480, so I'm not going to do it again. This, you work it out, is the expected value of Y given Z equal to 1 minus the expected value of Y given Z equal to 0 divided by the expected value of D given Z equal to 1 minus expected value of D given Z equal to 0. This, we discussed before, is called the wall estimate. Okay. And the main result, which again, we proved in 480, is that you work out this expression and then you show that is the average treatment effect conditional on those individuals that have D1 equal to 1 and D0 equal to 0, which you can also write as, D1 greater than D0, given that we are in the binary case. And these are called, is a local effect because it only affects a certain subgroup of the population. And that's why you call this late. The local average treatment effect, okay? Or is the average treatment effect for this group of people over here that are called the compliers, okay? Those that choose D equal to 1 when Z is equal to 1, choose D0 equal to 0 when Z is equal to 0, okay? So an example that typically people use to say what this means in an application is, a randomized control trial where, you give individuals a medication that they're supposed to take, say, at night at home, okay? And so Z equal to 1 or 0 is whether you offer the units the medication or not, the patients. D is whether they decide to take the medication at night or not, right? So some people will just refuse, they will forget, and for whatever reason, they will just not do it. And this is saying that compliers are those that when you give them the medication, they take it. But if you do not give them the medication, they're not going to go out of their ways to the black market, say, and try to find this medication and take it. Okay? These are compliers. They do it only if you give it to them. So, of course, we can define other groups. And the one that matters for us right now is the defiers. The defiers are these individuals. These are, people that are difficult. These are the ones that if you give them the medication, they don't take it. But if you just don't give them the medication, they just go out of their way, they find it, and then take it. Okay? And so monotonicity tells you there are no defiers. Okay? And so I wrote here random experimentation with partial compliance. So there are settings in which monotonicity is an assumption that is very easy to believe. For example, in cases in which like the medication that they're giving you is not available outside of from the experiment, right? So they give you the medication, you may take it or not, okay? But if you're not part of the experiment, you can now go and get the medication from the outside. And so that's a case in which this essentially will happen. So it should be clear that there are many settings, okay, in particular related to experiments, where monotonicity, is kind of like easy to defend. That doesn't mean that you can just go and defend monotonicity everywhere. And one of, I wrote before, misinterpret of misuse, is that one thing that calls my attention sometimes when I see papers using late is that they are explicit about the fact that they're assuming monotonicity, but very rarely they're discussed what monotonicity means in the context of their application, okay? What does it mean in terms of behavior? What are you exactly ruling out? That discussion is rarely there. All right. So there's one case that allows us to interpret late in an easy way, which is called one-sided non-compliance, okay? Suppose that only agents with Z equal to 1 can have D1. This is exactly what I said before. Suppose that you're just participating in this experiment as this experimental drug. You can take the drug if you participate in the experiment, but if you just do not get the drug as part of the experiment, you can just not go and get the drug from somewhere else. That's called one-sided compliance. There's one side you don't care about, because people cannot get the drug outside on the market. Okay. So in other words, you can have Z1 and D0. You can have somebody that you offer the drug, but the person decides not to take the drug. But you cannot have this. You cannot have somebody who is not offered the drug, but decides to take the drug because this person cannot get the drug from anywhere else. That's one-sided non-compliance. This is, as I said, common in certain types of trial. So, and this is a case where you can understand the power of late and what it estimates. And in particular, in this case, you can show that late, okay, is equal to the average treatment on the treated. And you can see that because when you look at the group of individuals that are treated, that is D equal to 1, well, D equals to 1, okay, has D01 and D11 and D00 and D11. You cannot have D10 and D01 because it's ruled out by the one-sided compliance. So these are the only two things that you can have. What you have then is that the individuals that are treated in this particular case are exactly the compliers. And so when you look at the average treatment on the treated, which remember was the expected value of Y1 minus Y0 conditional on E equal to 1, well, this is the same as the expected value of Y1 minus Y0 conditional on D1 greater than D0, which are the compliers. And if you do the same for the opposite case, and you just focus on the people that are untreated, you can show that the late here is just going to be equal to the average treated on the untreated. Okay? Would be depending on the setting that you are. Sorry, I got confused with what I have written before for a second. I was distracted thinking that I had written monotonicity wrong, but then I realized no, that's why I got distracted. Hopefully, I wasn't confusing. Do you have any questions about this? No. All right. So, one thing is that you can identify in this late framework is the distribution of outcomes for compliers. Okay. Remember, I'm going to define here the choice types. Compliers, individuals have D1 greater than D0, meaning this. Defiers, individuals have D0 greater than D1, probability 0 under monotonicity. Always takers are individuals that always get D1 regardless of whether you give them the treatment or not. And never takers are individuals that get D0 regardless of whether you give them Z equal to 1 or not. And so we're going to define T as the type as always takers, never takers, and compliers. Okay? And so you can show, which again, I'm not going to show here today, but I want to discuss this, the distribution of the potential outcome. Let me just focus on Y1. Distribution of potential outcome Y1 conditional on the type, okay? When you condition on compliers, okay? Then is the distribution of Y, the observed Y, conditional on D times on DZ, okay? Where D is 1 and Z is 1, times the probability that the type is a complier or an always taker divided by the probability that the type is a complier minus this distribution where you have D1 and Z equal to 0 times the probability that you have the type is an always taker divided by the probability that the type is a complier. And so the intuition of this, in a way, is that you can sort of like difference out the always, or never takers, because if you just look at the individual have D1 and C equal to 1, and then you sort of like, as I said, difference out the individual have D1 and C equal to 0. Well, these guys over here have to be either the compliers or the always takers, okay, which are the only ones that will give us D equal to 1. And these guys over here have to be the always takers because they have Z equal to 0 and D equal to 1. And so when you look at this, essentially, you say that in a way you can difference out the distribution of compliers. So what if you have multiple instruments? As I said, the nicest way and cleanest representation of late happens in the case where you have a binary treatment and a very binary instrument. But what if you have a discrete instrument that you have that takes L values, okay? Or if you have multiple binary instruments and so on. we're gonna assume exogeneity as before. Now we're gonna be needing this instrument to be independent of all the possible potential treatments, and now go from 0 to DL. And then monotonicity is just gonna say, sort these values of Z, and then tell me that um, D, whenever you chose, like, D is still here gonna be, say, binary, or later we see it could take other values, but for now it's gonna be binary. But then whenever you chose, say, 1 for a given value of Z, you're gonna be choosing 1 for any value of Z that is higher than that one. Okay. So what you can see is that when you look at this representation over here, this allows you to reorder the values of the instruments. So without, because, I just labeled them 0, 1 through L. So that's arbitrary. And then given this ordering, this assumption over here, you can just define the propensity score, okay, which is the probability that D equals to 1, conditional on Z equal to little z. And then this assumption of monotonicity over here, dz prime greater than or equal than dz, is if and only if the propensity score at C prime is greater than or equal than the propensity score at C. Okay, so essentially you can relabel the values of your instrument from 0 to L according to the propensity score. And whenever people have multiple values of this instrument, they're typically going to be sorted in this particular manner. Again, because the numbers of the Z's are labels, so it is commonly the case you're just going to label them an increasing value of the propensity score. All right. Now that you have this, and then we're going to have the values of C sorted by the increasing values of the propensity score, what you're going to do is consider a two-stage least square regression, where you're going to include the indicators of Z equal to each of these values from 0 to L as instruments. So you're going to have L instruments, one indicator for each value of the Z. Okay. And so when you just look at the first stage, which is the regression of D on all these instruments, where these instruments are just going to be the indicators, this is going to give us the propensity score. The first stage regression of D on this is just going to give us the propensity score at each of these values. And then in the two-stage least squares estimator, we're going to have that the estimate is just going to be equal to the covariance of Y given the propensity, covariance between Y and the propensity score divided by the covariance of D and the propensity score. And now the tedious part, okay, is you work out this expression and you're going to show that beta two-stage least squares is essentially a weighted average of pairwise lates from m-1 to m, where these pairwise lates are the cases in which you condition on those individuals that change their decision when the instrument moved from the value m to the value, from the value m-1 to the value m. And the weights, okay, are given by this expression over here that has to do with the propensity scores. So this is in the problem set. It's not as ugly as it looks, okay? So you're going to work it out and see. But the reason why I wanted to work it out, this is because, when you do it, you're going to learn how the mechanics work in the background. And then it's going to hopefully force you to see how the minute that you deviate from the binary instrument case, yes, it's true that people will say, like, oh, it's a weighted average of lates, okay? And it's true that these weights are positive, as I wrote here. So this is nice because, again, if, for example, the sign of this, if all these are positive, this is going to be positive and the like, okay? But it is still sort of like you're not choosing the weights. The weights are given by construction, okay? Why these weights matter is something that could be up for discussion, okay? Because it's not really clear that you really care about this. And then, each of the pairwise lates actually do make sense if you think about it, because you're just focusing on those individuals that are affected by the change from this instrument. And remember that an individual will be affected by the monotonicity assumption only by one of these changes, right? Because the minute that chose D equals to 1 whenever Z was value 3, you're going to choose D1 for 4, 5, 6, and so on. Anyway, in addition, I think it serves to show that this expression over here is way less clean and transparent than the one that you obtain in the binary C case. Okay, so um, something to think about. But if you ask me, then you just go and look at a number of papers where you're going to see that they have instruments that take multiple values, and the paper will just say like, "Oh, the two-stage least square is just a weighted average of lates," which is true. Is this? Then when you look at the number, you want to interpret it, it becomes um, less clean for sure. Now, we already got this idea that it's not as clean when we had multiple instruments. Now we're going to add covariates, okay? And the first thing we could do is to say, okay, let's just add the covariates non-parametrically, okay? So the idea is that you want to add more stuff because, again, this idea of controlling for other things, so it's always present. People have observed covariates, they want to use them for their analysis. And so we're going to adjust everything now conditional on X. We're going to go back to the binary case. We're going to assume that the instrument is independent of all this conditional on X. This makes the requirement that we have on the instrument weaker now because we're requiring dependence only conditional on certain types of groups, okay? Then we're going to ask for relevance. And now relevance is just going to require this almost surely because we're conditioning on X here on both sides. Monotonicity is going to be the same, almost surely, conditional on X. And we're going to have this condition of overlap. Okay, we need the instrument to take values 0 and 1 for each of these, say, groups. Okay, for each of the values of X. So if you condition on X, you're going to have exactly the same thing that we had before. You can just go and do it. It's just exactly the same, except that everything is conditional on X. Exactly the same argument, the same thing. You identify the average treatment effect for those individuals that are compliers, conditional on a given value of X. And this is the conditional late, okay? And now you can integrate over this over X, and then you're going to have the same late parameter. And that's how you account for covariates. The problem is that, as you know, we have problems with the non-parametric approach whenever you're conditioning a lot of things. And that is typically called the curse of dimensionality, which, remember, it will affect, for example, the rate of convergence of the estimators that we're dealing, and may even affect even computational tractability of the approach. So something that is more standard is that people will just include the covariates linearly as usual, and they will just do two-stage least squares. And so the question is like, okay, now we can go back and think in exactly the same way as we did with late when we started thinking about IB. We said like, well, we know how to do IB. What's the interpretation of IB in this heterogeneous model? We worked it out. It was late under some assumptions, and that was nice. But we can do the same here. We could just run a two-stage least square regression of Y on D using the instrument Z and including all these covariates linearly. And ask the question, is the two-stage least square estimate, okay, does this two-stage least square estimate has a nice interpretation under unobserved heterogeneity? And the answer in general is no. It becomes messy. And in particular, consider this case, okay, where the answer is yes. Okay, suppose that X is discrete, and we're going to write it as a set of binary indicators. So suppose that X takes 3 values. We're going to take the indicator that is equal to 1, indicator is equal to 2, indicator that is equal to 3. Okay. The excluded instruments are going to be X and X times Z. And we're going to assume for simplicity now that Z is binary again. Okay. And then, then we're going to run a two-stage least squares. I wrote here, notice that it's not fully saturated because I'm not including the interactions between these covariates and the variable that we care about, D. It's just Y on D and X, okay? But we're going to include X and XZ as instrument. Then the two-stage least squares estimate in this case takes this particular form. And it is a weighted average of lates, okay? And it assigns more weight to individuals that have more residual Z variation, as you can see from this expression over here. However, notice that the expression is already complicated And notice all the things that I had to assume to get this like cleaner representation. Okay, in particular that this is discrete, that this is binary, and that you're doing the regression in this particular way. So the moral is that in general, when you have axis, it's not really easy to interpret the two-stage least squares estimate. But as always, there's gonna be a way of interpreting beta two-stage least squares in a nice way, and you see people use it. So say, well, what's the argument? There's an argument that we're gonna see next. Let me recap now. So the estimates, okay, we learned this word today, estimate. The IB estimate in the binary D, binary Z case is the late. We know that. The parameter is easy to interpret as the average effect for compliers, and it could be quite relevant for policy intervention that affects compliers. So it just matters whether in your application, the group of people that are qualified as compliers are people that you care about, that matter, that are well represented, and whether monotonicity makes sense in the case or the application that you're considering. Two-stage least squares, on the other hand, is a mess, okay? Even in cases that are really specialized, like the case over here, you can see how now it just starts looking kind of like weird. And, it's a weighted average of several different complier groups, which also makes it like hard to interpret. And then these weights over here, even though they sometimes make sense from, say, a statistical point of view, is the variance of this divided by the expected variance of that, or things like that. And when you think about it from a conceptual point of view, why you're weighting more people than other, they make less sense. Okay. As I said before, these results are motivated by backward thought process. Let's just first tell me what we know how to do, and then let's try to see if we can interpret what we know what to do in a more sophisticated setting. Okay. And then later on, towards the end of this first part of the class, we're going to try to do the opposite. We're going to try to say, what are the parameters that we care about? Can we use things like IB or least squares to say something about those parameters? And it's going to be a different approach, but we're going to get answers there. All right, before I move to about this kappa, which is going to be the way to salvage in a way two-stage least squares, are there any questions up to here? All right, let me recap because we derail a bit. We're talking about adding covariates, and then the summary is that adding covariates is a mess, okay? So can we do it in a better way? And this was done in Abadi's paper. This 2003 paper, he called it kappa, and people call it now Abadi's kappa, okay? So that's why another reason why you should be careful about the letters that you choose, right? I always tell my students and whatever, be very careful with your notation. Okay, then imagine you write a paper, you think nobody's going to read, and everybody reads it, and now they use a letter that you chose, okay? Good, thanks God that Abadi chose a kappa, because imagine you use some weird letter, and then people start using that weird letter. So anyway, so the idea here is we're going to add covariates, okay? And we're going to stick to the case where D and Z is binary. Okay, I wrote here an elegant approach to deal with covariates that is going to make things very simple. Okay, and so the idea is that we're going to run regressions only on the set of compliers. Suppose that I have a compliers indicator, I can just run regressions on compliers and call it a day. The problem that makes that difficult is that compliers aren't directly observable, as we know. Okay, but the idea here is that Abadi found a trick where you just wait, and then you essentially only put positive weights on the compliers. And this is the idea. Abadi showed that for any function g, which is just a function of y, x, and d, okay, the expected value of g conditional on the type being a complier is 1 over the probability you're a complier times the expected value of kappa times g. And kappa here is just 1 minus d times 1 minus z divided by the probability of z conditional on x, minus 1 minus z times z divided by the probability of z equal to 1 conditional on x. So notice that kappa is known in the numerator and, has this conditional probabilities in the denominator that you can estimate, okay? So these are maybe unknown, but it's just the probability of z given x, probability of z given x. So intuitively, and this is really sketchy, but still I like to think about it like this, you can say that the compliers here are 1 minus the always takers and the never takers, because under monotonicity, there are no defiers. And so on average, this kappa only applies positive weights to the compliers, because it's just now go and compute the expected value of kappa conditional on any type, x, d, and y. This delivers the indicator that the type is a complier, regardless of whether you hear condition on always takers, never takers. Okay, it always gives the indicator whether T is a complier. So what is this saying? This kappa in expectation puts weight 1 if you're a complier, 0 if you're an always takers or a never taker. So on average, kappa times G is only positive for compliers. That's what's going on. And so how do you exploit this for estimation? Well, take the difference of squares of your function G, okay? So this is saying if you just minimize the square residual, okay, which you would do, say, if you were solving two-stage least squares or least squares if there was no endogeneity, this type of criterion function, conditional on being a complier, this is the same as minimizing the same problem where you are just weighting everything by kappa. So this is a weighted least squares problem. And so now, as I said, kappa, well, let me just not jump ahead. So I say estimate alpha and beta about solving a sample analog of this second problem. This is a weighted regression that requires these weights kappa, and you can estimate these weight kappas easily. Okay, and this result, as I wrote here, is general enough to use in many other estimators like maximum likelihood and so on, but when here, we'll just use it for two-stage least squares. Okay, and so to implement the result, one might estimate kappa, and this we need the probability of z equal to 1 conditional on x. We need only one of this because this is probability of 0, it's just 1 minus the probability of z equal to 1. And this, okay, is the only object that we need to estimate. You can use any model. This is a prediction problem we discussed last time, and you can use any prediction tool that you choose to do this. But the cool result is that if p of z equal to z equals 1 condition x is linear, then this kappa weighted linear regression equals exactly two-stage least squares. Okay, and so we know that this, in theory, cannot be linear, right? Because if it just plot, suppose that x is scalar, right, and then you have z over here, and then you plot the probability of z condition on x, typically it will look something like this. If it's linear, it will cross, I'm trying to say 1 and 0, right? So it has to be something that avoids this crossing 0 and 1. So strictly speaking, it's not going to be linear. So you can think about logit, probit, or these type of models. However, in practice, all these models, except when you're at the tails, okay, tend to be roughly kind of like linear in the middle, okay? And that's why like logit, probit, and even linear probability models are used so often in practice. And so in reality, this approach proposed by Abadi tends to often give results that are very similar to two-stage least squares. And here comes the magic. Then this is the reason why people then use two-stage least squares. Because they say, well, I could have used Abadi's kappa. Oh, well, Abadi's kappa typically gives numbers that are very similar to two-stage least squares. Yeah, it's just two-stage least squares. Then we go back to use what we want to from the beginning, which is let's stick to two-stage least squares and not bother. You're gonna do this in the problem set, okay? Questions? We're gonna go over this applied paper by Angus and Evans. It's a 98 paper, and so it's about the relationship between fertility decisions and female labor supply. We know that there's a strong negative correlation, okay? But as I wrote here, this is joint choices, right? So it could be, that women that have a lot of kids decide to not to work because they have a lot of kids. Or it could be that they decide to have a lot of kids because they knew that the opportunity cost is just very low. And so these are both decisions, having kids and participating in the labor supply. So when you want to find this effect, you have to be careful about understanding that something that selection on observables is not going to work. Okay, So what's the empirical strategy in this paper? Y is a labor market outcome. Okay, it could be salary, or we're going to see some of them, but there's some form of measuring the labor market, and we're going to restrict the sample to women. Okay, with 2 or more children. Okay, and this is going to be an indicator for having 2 children versus 3 or more. So the idea is that you get rid of the ones that have 1 children, because it could be that some people have preferences for having 1 versus more than 1. And then the idea is that once you have more than 1, having the third one is just has to do perhaps with a similar type of decision. The instrument is just going to be 1 if the first 2 children had the same sex. Okay. And this is based on the idea that there are preferences for a mix of boys and girls. Okay. And so there's another instrument. There are 2 instruments, going back to something that we discussed before. Okay, we have more than 1 instrument, while here we have 2. Z here is 1 if the second birth was a twin. Okay, which can tell you that the reason why you got 3 was exogenous; it wasn't endogenous. Okay, but this has issues for there are issues about this for other reasons that we're going to explain. So exogeneity requires the assumption that sex at birth is randomly assigned. Let's say we maybe leave this. Okay, sounds reasonable. The twins instruments is less compelling than the other one, in particular because we know that the older the age of the man and the father as well, the higher the probability that you have twins. So now suddenly, if you're conditioning on twins, you may be conditioning on people that are older age, and people in older age made certain choices. Okay. Also, because as I wrote here, it impacts both the number and spacing of children. Okay, if you don't have children, you may not know, but if having 2 babies in the house is not the same as having 1 for sure. And I had 2 sequentially. I wouldn't have been happy probably with 2 simultaneously. But anyway. And then monotonicity. So here, what is monotonicity? Monotonicity restricts preferences, heterogeneity. Here, I would say in unattractive ways, even if you believe these stories, right? Because what you're saying here, the instrument, remember, is like, go back, as see 1 if the first 2 children had the same sex, okay? And so you're essentially saying, whoops, here D1 is greater than or equal than D0. Okay. So if you had 2 kids that had the same sex, and your decision to have, and you decide to have the third one, you would have definitely, sorry, it was the opposite. If you had 2 kids that were different sex, okay, and you decided to have this third one, you would have definitely had a third one if both kids were the same sex. So this is removing monotonicity. Okay, people that had a taste for having 2 boys or 2 girls. Okay, again, you can defend that, and I'm not against defending that. I'm pointing out that these are the type of discussions that when you're presenting applied work, you should have. Okay, because they're part of like translating the assumptions that the econometric method requires to what they mean in the setting that you care about. In this paper, unfortunately, I wrote here, there's no discussion about this. And as I said before, it is common to see papers where they just assume monotonicity without describing what it means in terms of behavior in the paper. Anyway. So the authors do the usual thing about exogeneity, in particular trying to say that sex at birth is random. And then they just, use the usual balance test on certain covariates: age, black, white, years of education. And then you use a usual t-test, difference of means, okay? And they claim, look, all these are just, you cannot reject that they're equal to 0. In the twins case, that is less clear because you have cases in which that is not the case, like here. And then, as I wrote here, twins is well known to be correlated with age. And then you just see that over here, where if you just do a simple t-test, okay, you can see that the age is higher for those that have twins relative to those that don't. But that's the first table. Then we get to this, which is more interesting, okay? Because this puts together what we learn in class. So remember that we had 2 instruments here. One is the instrument that is more than 2 children. Okay, 1 if you have more than 2 children, 0 if not. And then there's another one that is just the number of children. Okay, which we are um wait, no, I said it wrong. Um these are the D's, okay? More than 2 children is the D. Remember, D is 1 if you use more than 2 children, and 0 otherwise. And the other one is a discrete D, which is the number of children. So, but then here, this is the mean difference by same sex, okay? And this is exactly as I wrote here, the denominator in the Wall's statistic that we define. Then, if you just look at this piece of the table, you have the difference, by the instrument of all these different measures of outputs. And this is the numerator in the Wall estimate that we wrote before. The expected value of y conditional on z equals 1 minus expected value of y conditional on z equals 0. These are the numerators. And then when you take the ratio of this over this, okay, you get, so for example, the negative 0.13 is just this guy divided by this guy. That's the Wall estimator or the IB estimator. Okay. So in this table, you have all these pieces that gives you the construction exactly following the steps that we said before. These are just IB, and these are the lates. Okay. And then depending on the outcome that you look at, and depending on whether you use this D or this other D, then you have the slightly different values, but they're like mostly aligned. So now, if you just, instead of looking at IB, you just look at least squares and you forget about endogeneity. Okay, so here in this table, you will run these dependent variables on the outcomes that you care about without instrumenting. And then you compare that with the IB that are here labeled as two-stage least squares. You're going to see that the differences are significant. So these differences are consistent with the idea that you have endogeneity or selection here, right? So if you really believe that these people are making decisions based on factors that you don't get to observe, then you would expect to see the difference between an approach that assumes that such thing doesn't happen with an approach that relies on the validity of the instrument as an alternative identification strategy. And then going back, okay, here, back to the question that I was asked before, you have two separate instruments, okay? Instead of same sex, you said 2 boys, 2 girls, okay? And here, there's an over-identification test. Again, mechanically, you're just doing two-stage least squares. Of course, you can do the over-identification test. The part that, to me, again, it's funny is, what's the interpretation of this in this case? And this is not discussed in this case, despite being standard practice, okay? But then if you look at these numbers in brackets over here, it presents, I think it says somewhere, brackets, over-identifying restriction. Okay. Oh, this is exactly what you guys asked me a couple of slides for. And here, because it's just the p-value. That's what I said. But, leaving that aside, the numbers, if you just look at them, are highly consistent between using this particular instrument as one of them or the two. And presumably that's what these researchers care about. So you're going to work, by the way, on the problem set that I'm going to release on Thursday on this particular application if you want to. So, debate. Angry, Simmons, and Rubin, it's a 96 paper, was in a special issue of JASA. Essentially, in a way, the article criticized econometric approaches, which is the latent variable notation, this like Roy model specification that I wrote earlier, and instead advocated for potential outcomes, okay, as a more credible approach. And late came as an example of how successful the late notation could be to describe the things that you want. Of course, that's why I wrote controversy and debate at the top. This created some problems, and there are articles that are commenting that main article in that same volume. So if you're interested, you can read that. Um, but as of today, I'm gonna say late is still a topic that I, I would say probably is one of the topics that creates the most extreme views about it. People that just love it and they just think that everything that they need is just about late, okay? And there are people that just hate it, okay, and then just don't want to even hear the word late, okay, to start with. Um, One issue which we discussed before is that the definition of the local average treatment effect depends on the instrument that you use. So this raises issues about external validity. Also, like when you think about the group of people that you can say something about, you know, in the case of in the example that we just saw, for example, which is individuals had got the first two kids with the same sex, is like, why is that a subgroup of the population that you care about? Sometimes it's clear, sometimes it's not. Okay. But what I wrote here, which I think is true, which is that this issue about late or yes or no to late, it's just part of a broader discussion and debate in econometrics and applied work that has to do with internal versus external validity. All right. So sometimes it's easy to have work that is really neat and has high internal validity, but you can't say anything outside that. And then sometimes you can have approaches that gives you much better external validity, but that require representations that perhaps are less elegant. And so there's a lot of discussions about this. Sometimes people, and this is the last thing I want to say today, probably, sometimes people refer to this as structural versus reduced form. I think this is misleading, personally, um, and I think that all this is structural. Everything that we talk today and even late is structural. And, structural versus reduced form doesn't clarify much of what happens. I think that the most important distinction is whether you have something that is structural or something that is just descriptive. Okay. Doing descriptive things, say predictions and projections that we discussed before, are things that you do when you do not want to talk about causality. You want to talk about counterfactuals, okay? But the minute that you do want to talk about counterfactuals and causality, I would say you belong to the structural camp. Sometimes people say like, well, this doesn't look structural because late just have like Y0, Y1, and D. Yeah, but this, like it or not, is kind of like structural model. It's imposing a structure, it's imposing tonicity, it's imposing how agents behave. So it's just a very simple one as opposed to something that you can use, for example, in IO, where you're going to model utilities and maximization of agents and so on. But then when you go back to the Roy model, I will frame it as a structural model because it's just telling you how behavior is determined for certain units in your analysis. Whereas whether it's reduced form, which is the typical terminology that people use when they run regressions, it's kind of like weird because you can just run regressions without any attempt to say anything causally, in which case you would be doing something descriptive, okay? But you could be running regressions trying to come up with policy um, uh, interpretations. And so I don't know. It's just a matter of, this again are labels. What matters is that you understand conceptually what it means one or the other one. But in IO, it would be normal for people to call reduced form just running a regression or doing it late or doing differences and differences. They're going to say reduced form because later on they're going to impose a model. But I would say these are two different types of structural approaches. But again, depends on who you talk to, what they'll say. Questions? That's the end of the class for today. That's all I have to say. So next class, we're going to start talking about marginal treatment effects. Let me know if there are questions now about this.